Hi, today I'm going to talk about vector valued functions. Let's first define this kind of function. For this, we have a subset of real numbers, and we have a vector space, and the function f from A to V is called vector valued function, and we may show a vector valued function in this form or equivalently in this form. Here, I, j, k are standard unit vectors, and we call the function f1, f2, and f3 the component functions of f. Okay, a domain of a vector valued function. Let's consider this vector valued function. Suppose the domains of component function f1, f2, and f3 are e1, e2, and e3 respectively. Then the domain of f of t is capital A equals to a1 intersect a2 intersect a3. Okay, let's provide an example. Finding the domain of f of t, et, t square. Solution: f1 of t equals to et, f2 t, and t square. And all of those, the functions are defined on the whole real numbers. Then our domain is the real numbers. Let's find the domain of this vector valued function, whose components are logarithm t, square root 1 minus t, and t. For logarithm, it's clearly the domain is the positive real numbers. And for the square root 1 minus t, our domain is this interval. And for the last component, the domain is the whole real numbers. Then the intersection of a1, a2, a3 is this closed interval. Some important points. Okay, let f and h two vector valued functions. Then the algebraic properties of those vector valued functions are defined similar to the algebraic properties of vectors, as you can see in these properties: vector summation, vector subtraction, and multiplication by a scalar. Okay. Limit of a vector valued function. The limit of a vector valued function is defined by the limits of the component real valued functions. Yes, those component functions are real valued. So we know very well how to take a limit for a real valued function. I mean, this part is familiar with us. So that's why a limit of vector valued function is the limits of the component functions. Okay. A limit of vector valued function exists if and only if those limits exist. Otherwise, namely, at least one of these limits is infinity, then we call that this function has no limit. By the way, we should emphasize that the limit of a vector valued function is again a vector valued function. Indeed, is here should be vector. As we can see in this example. Please look. Our vector valued function is defined et as first component, sine of t over t and t. Okay, let's consider the limit at the point 0. Here clearly 1, here clearly 1, and obviously 0. As you can see, it's another vector, belongs to the R3. By the way, I3 R Cartesian product R Cartesian product R. And continuity is similar to the limits. I mean, a vector valued function is continuous if and only if the function is defined, the limits exist, and the limit equals to the value of alpha, the function at the point alpha. Okay. An example. Let's discuss this vector continuity of this vector valued function. Components are t, constant 1, and 1 minus t square. Of course, it's defined at the point 0. Yes, 0, 1, 1. And the limits, those are the polynomials. T, the constant polynomial, polynomial of degree 2. So those have limits as well as continuous. And since the both equalities are same, we say ft is continuous at the point t equals to 0. Derivative of vector valued function. If you want to take a derivative of a vector valued function, then you have to take derivatives of components. And you can see in this example. Before example, we may see in this theorem the derivative of a vector valued function is the derivatives of components. Of course, this is also another vector valued function. A vector valued function is differentiable if and only if the components are differentiable at the same point. Okay. For this vector valued function, let's find the derivative. Yes, we have to take the derivatives of components, which is similar as you can see. Okay, some algebraic properties. You can dot product of two vector valued functions as in the usual formula, and you can cross product two vector valued function as you have done in the vectoral analysis. vectorial calculus, and a vector product of f and h that may be defined via the determinant formula. In order to take a determinant, firstly, we close the first column and row, and then we have a cross multiplication. Yes. And this line is an explicit formula for the cross product. An example, we have a vector valued function whose components are cosine t, sine of t, and 2 times t. And we are going to find the first and second derivatives and the dot product of first and second derivatives, the cross product of first and second derivatives. Okay, the first derivative and the second derivative is easy. We just take derivatives of components. Okay, and if we want to find the dot product of those vector valued functions, then we have such a multiplication, and we obtain a 0. Geometrically, this equality says that the first derivative is orthogonal or perpendicular to the second derivative. And cross product, if you apply the determinant formula, then you may easily obtain this vector valued function. As in a limit, continuity, or derivative of vector valued functions, integration is same. Namely, if you take integration of a vector valued function, then you have to integrate the component functions. Yes, such as this equality, which means that it's quite simple. Okay, our vector valued function root of degree 3 t, 1 over t plus 1, and e minus t. Okay, let's take define the integrals on the integration interval 0, 1. By the way, the integration interval 0, 1. Okay. As simple integrals, and if you substitute the values 1 and 0 into this line, after some calculations, some simple calculations, you may obtain this vector. By the way, a defined integral of a vector valued function is another vector, say PQR. Yes, we know already this fact. E.g., K are called standard unit vectors, and you may choose those 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, and norm or length of a vector valued function is defined by this equality. Of course, this statement is scalar. For an example, let ft be defined for cosine t, for sine of t, and 3. And the norm of this vector valued function is equal to 5, which means that every vector at any point t, the vector ft has a length 5. By the way, this value is independence of the value of t. Yes, which means that this vector valued function has a constant length. If this constant is 1, then we call it unit vector valued function. Of course, this is very specific properties. Okay. We already saw an example of orthogonality. Let's define formally. F and H be vector valued functions. If for each t, the dot product of F and H is 0, then it's said that F is orthogonal to H. Or we can say that F is perpendicular to H. Obviously, standard vectors standard vectors are unit and orthogonal or perpendicular, mutually orthogonal to each other. If f and h, two vector valued functions, and their vector product is 0, then those are parallel or linearly dependent. Let's consider two constant vectors and show that f is not parallel to h. We may show that if their cross product is different 0, then those are not parallel, and you can easily see this vector obtained by the cross product of f and h is not 0, which means that f is not parallel to h. By the way, geometrically, the cross product of f and h is another vector, and geometrically, this vector, the perpendicular both f and h. Yes. Namely, if we draw here is f, let's say h, then this vector, the cross product of f and h. And the angle between f and h, f cross product h, and f or h is the right angle. Yes. This is the theorem we already proved. We haven't proved, but it's quite easily. It's quite easily because of the properties of the determinant. Yes, some another algebraic properties. This is obvious from the properties of determinant. Some another algebraic properties. Yes, if you dot product f and the cross product h and r, then you have this determinant. So as you can see, you can prove this theorem exactly these properties. By the way, the vector product is commutative. Some another algebraic properties. If you take dot product of a vector by itself, then you obtain squared norm. Yes, the obvious properties. The vectors f, h, and r lie in the same plane. Geometric. This is the geometric properties. If and only if this dot product is 0. As we emphasized before, h and r, two vectors, and if you take cross product then and obtain normal to the plane. Yes. Let's say h cross product r. So if f lies in the plane spanned by h and r, then it must be perpendicular to h cross product r, which is here. Okay, let's determine if three vectors lie in the same plane. By using this theorem. If their determinant is 0, it means that those are in the same plane. If you calculate, which is simple, you will see that is 0, which means that those are in the same plane. Some little physical terms, velocity and acceleration. Let f1, f2 twice differentiable functions of the parameter t, and f be a vector validity function. f1i, f2g. By the way, we are in the plane. We are in r square. So this vector is the position vector of a particle which moves on a straight line, and the velocity of the first derivative and the acceleration is the second derivative. And by the notion of speed, we understand the norm of the first derivative. By the way, here should be square plus f2, the derivative f2 square. Yes. Please pay attention here, not f1 square. f2 square, f1 derivative, f2 derivative square. Okay. An example. Let's find the velocity vector and speed and acceleration vector of a particle that moves along the plane curve C described by this vector valid function. Okay. And velocity vector is its first derivative, which is cosine of t over 2 minus sine of t over 2. If we take second derivative, we obtain that minus 1 over 2 multiply sine of t over 2 cosine of t over 2. So if we take norm of the velocity vector, then we obtain its speed, which is 1. By the way, if we take the norm of acceleration, then we obtain a scalar acceleration, which is 1 over 2. I'm sorry, 1 over 2. Yes, it's correct. By the way, if you via the computer programs, if you derive the vector valid functions, you can see that their graphs are the curves, and a length of a curve defined by a vector valid function is defined this integral, defined integral. So this vector valid function determines a curve in a tree space or in plane, it doesn't matter. And its interval, if its interval is this closed interval, then the length of this curve on the closed interval a comma b is defined this defined interval. Let's give an example. Let's C be a smooth curve defined by this vector valid function, and on the interval 0 to pi, let's find its length. Its first derivative, you see, the length is defined in the integral of the norm of the first derivative. Yes, first derivative is another vector valid function, and if you take norm, you can easily see that you have a constant 5, and its integral, it's equals to 5t, and the bounds are 2 pi and 0, so you have the length as 10 pi. And we have some geometrical objects on curves, defining by defining the derivatives of vector valid function. Let's C be a curve and parameterized by this vector valid function. If f is differentiable, then the first derivative is continuous, and if the first derivative is non-vanishing on this interval, then we say the C is a smooth curve. Some example, smooth curves and non-smooth curve. By the way, this example is not very correct because this is an example of a self-intersect curve. So this figure says that the vector valid function f may be smooth, but is not how to say in English. I will remember the word. I may help from net. Yes, the correct word, one-to-one. Yes, one-to-one. Let's properly write. Okay. Such a curve may be submitted. Okay, at the moment I have some problems about my computer. Just a moment. Yes. Which is good now. Make it smooth, but not one-to-one. Okay. I mean, it's not a good example. A non-smooth figures may be like yes. Those are the some points that the function f, the vector valued function f is not differentiable. Okay. The first derivative of the vector valued function f is a tangent, the vector field of the curve. Let's say f prime, and here is f. Yeah, it's tangent. Let's define properly. Let C be a smooth curve denoted by f on an open interval I. Then the unit tangent vector to the curve C is denoted by that formula. Is a unit vector, is a unit tangent vector. Okay, an example. Our vector valued function f of t, whose components are t and t square. Of course, we may assume that this curve is in a plane, and its first derivative 1 and 2 times t, and its norm square root 1 plus 4 t square, and its tangent vector field is parametrically in that form. And at the point 1, we have this vector, this unit vector, and geometrically this vector, this is by the way, this is a parametric equation of a parabola. So this is the tangent vector at the to parabola at the point t equals to 1. Yeah, in Cartesian form, as you can see, this curve given in explicit form y equals to x square, which is a parabola. A unit vector field, let C be a smooth curve denoted by the vector valued function f. Okay, if its acceleration is not 0, then the unit normal vector to the curve C at the point t is defined by this equality. By the way, this formula, let's write here note. Just a moment. Okay. Finally, this formula is true only if the vector valid function f of t has constant speed, namely f prime Yes, the norm of the first derivative of the function f is constant. In case this condition, yes, this is the unit normal of the curve C. Otherwise, namely, if its speed is a function, then this formula doesn't hold. Okay, find unit normal vector for the curve, a special curve helix. Helix is a curve that its projection onto the plane spanned by I and G is a circle. Yes, this is a circular helix. For this helix, let's find the tangent vector, which is the first derivative. And if you make its unit, then you have to divide it by its norm, as in this equality. And the normal vector, it's the acceleration of the function f, which is the second derivative, as you can see. And if you want to make its unit, then you have to divide again by its norm. Then you are going to find this unit vector. Yes, the geometrically normal, the perpendicular to the the tangent. Here is tangent, let's say t, and geometrically n is perpendicular to the tangent vector t. Here is the second derivative of f. But as I said before, this fact holds only if constant. Okay. B normal vector, CB azimuth curve, denoted by the function f of t. Then the B normal vector to the curve C is defined by this equality, namely the cross product of t, the tangent and norm. It's clearly the B normal vector is perpendicular both t and n. Okay, we have an vector valid function cosine t, and square root 2 sine t. Let's find tangent, normal, and binormal vectors at the point t equals to pi over t. Okay, we have to find the second derivatives, the first derivative for t and the second derivative for n. Yes, this is the second derivative. This is the first derivative. Okay. And the value of the tangent vector at the point pi over 2 is this. Yes. And the second derivative and its norm and the value of unit normal at pi over 2 is this. And then finally we have the cross product T and A obtaining this vector. Yes, geometrically you may see the vectors T and B and situated at the point and T of the curve C. Yes, you may solve these problems by yourself. A curvature of a smooth curve. In this section, we want to briefly discuss the curvature of a smooth curve, which is parameterized this vector valued function. If the velocity vector is not zero, then it's we may say, as emphasized before, is a smooth curve, or in some books it's called a regular curve. And to find the curvature, we have two formulas. Here is equals to easily the norm of the second derivative of the vector valued function f. If this equality holds, if one, namely, has a unit speed. Otherwise, you can use this formula. The second formula is valid always, but its first formula is easy, but may be used in a special case. Namely, the vector valued function has unit speed. So, by the way, here is not equals to this one. Here is yes. Of course, if this one, then it reduced to do the directly the norm of the acceleration. Okay, let's consider the example. Okay, the curve C is given by this function, namely t, 3 sine t, 3 cosine t. So let's consider if it has constant speed, and the first derivative and its norm is constant. So you may use the first formula. This is the tangent vector. This is the second derivative. And the norm of second derivative. Okay. If you divide the norm of second derivative by speed, then you obtain this. Okay, another example. And another smooth curve defined by this vector valued function. As you can see, the coefficient of g is 0. We may use second formula because if you calculate, you may see that the norm of first derivative is not constant, so you have to use second formula. Okay, the first derivative, second derivative, and the cross products. Those are the simple calculations. That is why I may omit. Yes. And the norm of this cross product is 2. And the speed is square root 4t squared plus 1. Then curvature is found by using the second formula. And the curvature is given this equality. So if you want to find curvature of a curve in, of course, this formula, let me clearly. Okay. This formula is valid always. In any case, you can use this formula, but this formula is also a restriction. You may use this formula only in three-dimensional case. Okay, and this formula holds only if the curve has constant speed. So you can keep the second formula in your mind, and you may use always this formula, of course, if you are in R3. And for multivariable functions, we will start this section in next video.